You know what I find absolutely mind-blowing, Max? The fact that we can now have robots that understand internet memes.
Wait, what? Are you saying robots are now scrolling through Reddit during their downtime?
Not exactly, but this new research from Google might be the next best thing. They figured out how to take all that knowledge from the internet and use it to help robots understand the world in a much more human way.
Oh, you're talking about that RT-2 paper, where they basically taught robots to think using the same models that power things like ChatGPT?
Exactly. Welcome everyone to another episode of Totally Unprofessional Peer Review. I'm Casey Park, your resident developer with an eye for structure and flow.
And I'm Max Stone, the theorist who's always nitpicking about metrics and methodology. Great to be back with all of you listeners.
Today we're diving into a fascinating paper titled RT-2, Vision Language Action Models Transfer Web Knowledge to Robotic Control. It's all about how researchers are teaching robots to leverage the vast knowledge contained in internet-scale vision language models.
What makes this work really interesting is their approach. Instead of building separate systems for language understanding and robotic control, they've found a way to express robot actions as text tokens, essentially teaching the same model to both understand language and control robots.
And the results are pretty remarkable. These robots can generalize to new objects they've never seen before, interpret commands that weren't in their training data, and even perform basic reasoning tasks.
Like figuring out which object would make a good improvised hammer. Spoiler alert, the robot chose a rock, not a banana.
I'm particularly excited about how this bridges the gap between large language models and embodied AI. We're starting to see robots that can actually understand the semantic meaning behind commands, not just follow pre-programmed instructions.
And get this, they can even respond to instructions like pick up the object closest to the cups or grab the largest balls without being explicitly trained on spatial reasoning concepts.
It's like they're developing common sense, which has been one of the hardest things to program into AI systems. So today, we'll break down how RT-2 integrates these vision language models into robotic control, examine their novel approach to expressing actions as text, and explore these emerging capabilities that honestly seem almost magical.
And we'll try to figure out if this is actually a breakthrough that will change robotics forever, or if there are fundamental limitations we need to be aware of. Because let's be honest, a robot that can identify an energy drink when asked for something to help with tiredness is impressive. But how far can this really go?
Let's dive into what makes this RT-2 approach so groundbreaking. At its core, we're talking about vision language. Action models, or VLAs. These are essentially robots that can understand what they see and what you tell them, and then take appropriate physical actions.
Right, and what's fascinating is how they're bridging the gap between internet-scale knowledge and physical robot control. Previous approaches typically had separate systems, one for understanding language and vision, and another completely different system for controlling the robot's movements.
Exactly. Let me show you a diagram from the paper that illustrates this beautifully. As you can see, RT-2 combines two types of data during training: internet-scale visual question answering data, which you can see on the left, and robot action data. The magic happens in the middle, where they integrate these into a unified model.
That's a key distinction from previous approaches. Instead of just using language models to act as high-level planners that tell separate low-level controllers what to do, RT-2 actually incorporates the rich semantic knowledge from internet-scale models directly into the control system itself.
Absolutely. And if you look at the diagram, you'll notice they're using established vision language models as their foundation. The paper mentions they adapted two previously proposed VLMs, PAL-IX and PALM-E, creating what they call RT-2 PAL-IX and RT-2 PAL-I-E.
These are massive models too. The paper mentions their largest model uses 55 billion parameters. That's not something you can just run on a standard robot processor.
Definitely not. But what's clever about their approach is how they represent robot actions. If we look back at the diagram, you can see they're treating robot movements as just another form of language. Notice how in the bottom left, they show robot actions like translation and rotation being represented as text tokens. Translation, double double one, double double two is and rotation, 10 double 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 10 w double tie and double double 10 w's. This is the key innovation that allows them to integrate everything into one model.
And that's brilliant because it means the model can be trained on both types of data simultaneously. The paper specifically mentions they use co-fine tuning, training on both robotic trajectory data and internet-scale vision language tasks like visual question answering at the same time.
Let's take another look at the diagram to understand this co-fine tuning process. You can see it in the middle section where they're feeding both types of data into the RT-2 model.
And the researchers found that this co-fine tuning approach is actually critical. They mention in the paper that if you only fine-tune on robot data, the model starts to forget all the rich semantic knowledge it learned from the internet data. By continuing to train on both, the model maintains its broad understanding while learning specific robot control tasks.
Right. And once training is complete, look at the right side of the diagram. During actual robot operation, the system takes in visual input, processes it through the model, generates those text token actions, and then de-tokenizes them into actual robot movements.
What's particularly interesting is that these models aren't just learning to mimic specific movements, they're actually transferring semantic understanding from their internet training. The paper specifically says they don't expect the transfer to enable new robotic motions, but they do expect semantic and visual concepts to transfer effectively.
And that's what makes this approach so powerful. By leveraging these pre-trained vision language models, the robots inherit all that knowledge about objects, relationships, and concepts that would be impossible to program explicitly or learn from limited robot training data alone.
Though it's worth noting, there are some practical challenges. The paper mentions that the computational cost of these models is high, which could become a bottleneck for applications requiring high-frequency control.
True, but they did manage to get them running in real time for their experiments, which is impressive given the size of these models. And the benefits are substantial. The paper reports that their largest models showed the best generalization performance.
That's the trade-off, I suppose. And it's worth mentioning that this approach puts robot learning in a really interesting position. As vision language models continue to improve, robots using this VLA approach should automatically benefit from those advancements.
Exactly. It's a simple yet powerful idea. By treating robot actions as just another language to be learned alongside visual understanding, we're creating systems that can leverage the vast knowledge contained in internet-scale models to make robots smarter and more adaptable.
Let's dig deeper into how they actually implemented this text token approach. The paper mentions that they convert robot actions into strings of numbers that the model can learn to generate.
Right. For example, they might represent a robot action as something like 11289124152127, just a string of numbers that encode the specific movements the robot should make.
And what's clever is that they format the input in a standard visual question answering format. So they'd ask something like, Q, what action should the robot take to pick up the cup? A, and then the model generates those action tokens as the answer.
Exactly. It's treating robot control as just another form of question answering. And this approach allows them to leverage existing vision language models without having to design new architectures from scratch.
The paper specifically mentions they adapted two previously proposed vision language models, PAL-I-X and PAL-M-E. These are models that were already trained on massive internet-scale data.
And that's a key advantage. They didn't have to build and train these huge models from scratch. Instead, they took models that had already been trained at great computational expense and adapted them for robot control.
I found it interesting that they mentioned different tokenization schemes for different models. For the simpler language table dataset, they used a format like XY, where X and Y represent 2D movements between 10 and plus 10.
And for the more complex real-world robot tasks, they use longer strings of tokens to represent the full 6 degrees of freedom movements, translation, and rotation in 3D space.
Let's take a look at some of their experimental results. This table shows how their RT-2 PALI-3B model performed on the language table benchmark compared to previous approaches.
Wow, that's impressive. Their approach achieved a 90% success rate, which is significantly better than previous methods like RT-1 at 74% and LAVA at 77%.
And what's particularly interesting is that this improvement comes largely from the transfer of knowledge from internet-scale pre-training, not from any fundamental changes to the robot control algorithm itself.
Now let's look at another important aspect of their approach, the co-fine-tuning process. The researchers found that it wasn't enough to just fine-tune these models on robot data alone.
Right. They discovered that if they only trained on robot actions, the models would start to forget all that rich semantic knowledge they had learned from internet data. So they had to keep training on both types of data simultaneously.
Let's take a look at this figure from the paper that shows how different training approaches affected performance.
This is really telling. On the right side, we can see 3 different training approaches: training from scratch in red, fine-tuning on robot data only in green, and their co-fine-tuning approach in blue.
And the co-fine-tuning approach clearly outperforms the others, especially when it comes to generalizing to unseen objects, backgrounds, and environments. This is crucial for real-world robotics, where you can't possibly train on every scenario a robot might encounter.
The left side of the figure is interesting too. It shows how their approach compares to previous methods on tasks requiring symbol understanding, reasoning, and human recognition. The blue bars representing RT-2 with PLI X55B are substantially taller across the board.
Another practical detail they mention is that during training, they balance the ratios of robot and web data by increasing the sampling weight on the robot dataset. This ensures the model doesn't just focus on general language tasks and neglect the robot control aspect.
And during inference, when the robot is actually operating, they constrain the output vocabulary to only valid action tokens when the model is prompted with a robot action task. This ensures the robot doesn't suddenly start generating poetry instead of picking up objects.
That's a good point. They also mentioned that the robot demonstration data they used was collected over 17 months in an office kitchen environment, with 13 robots performing various tasks. Each demonstration was annotated with natural language instructions describing the task.
So to summarize this novel approach, they're taking vision language models that were trained on internet-scale data, representing robot actions as text tokens, and then co-fine-tuning these models on both robot control tasks and visual question-answering tasks simultaneously.
And the beauty of this approach is its simplicity and effectiveness. They didn't need to design complex new architectures or training procedures. They just found a clever way to express robot actions in a format that existing vision language models could work with.
Exactly. And this unified output space, where both language responses and robot actions share the same format, enables the model weights to be entirely shared across language and action tasks. There's no need for separate model components that only handle actions.
It's a great example of how sometimes the most powerful innovations come from finding elegant ways to repurpose existing technologies rather than building everything from scratch. By treating robot control as just another language task, they've opened up a whole new approach to robotics.
And what's particularly exciting is that as vision language models continue to improve with more internet data and better training techniques, robots using this approach should automatically benefit without needing fundamental redesigns.
Absolutely. It creates this virtuous cycle where advances in language models directly translate to advances in robotics. And given how rapidly language models are improving, that's a very promising direction for the field.
Now that we understand their approach to expressing actions as text tokens and co-fine-tuning, let's move on to explore the emergent capabilities that resulted from this method, because that's where things get really interesting.
Now let's talk about what I think is the most fascinating part of this research, the emergent capabilities that RT-2 demonstrates. These are abilities that weren't explicitly programmed, but emerged naturally from the combination of internet-scale knowledge and robotic control.
Right. And when we say emergent capabilities, we're talking about behaviors that weren't present in the robot training data, but somehow appeared when the model was deployed. It's like the system learned skills that nobody taught it directly.
Exactly. Let's look at some examples from the paper. Figure 2 shows some really impressive capabilities that emerge from RT-2.
This figure is quite revealing. Look at these examples. Put strawberry into the correct bowl. Pick up the bag about to fall off the table. Move apple to Denver Nuggets. These are tasks that require understanding concepts that weren't in the robot training data.
What's impressive is that the robot can understand which bowl is correct for a strawberry, or recognize that a bag is about to fall, or even know what the Denver Nuggets logo looks like. All knowledge that came from its internet pre-training, not from robot-specific training.
And look at these examples in the bottom rows. Move Red Bull can to H, move soccer ball to basketball, move banana to Germany, and even move Coke can to Taylor Swift. The robot is demonstrating an understanding of letters, sports, countries, and even celebrities.
And my personal favorite, move banana to the sum of 2 plus 1. The robot actually has to do math to figure out where to place the banana. That's definitely not something explicitly taught in robot training data.
The researchers categorize these emergent capabilities into three main types: symbol understanding, reasoning, and human recognition. Let's look at how RT-2 performed in these categories compared to previous approaches.
This chart on the left really tells the story. The blue bars representing RT-2 with PLI X55B tower over the other approaches across all three categories. We're seeing success rates of around 80% for symbol understanding compared to less than 20% for previous methods like RT1 and VC1.
And the right side of this figure is equally important. It shows how different training approaches affected performance on generalization tasks. The blue bars representing co-fine-tuning significantly outperform models trained from scratch or fine-tuned only on robot data.
Let's take a closer look at the generalization capabilities. The paper shows examples of how RT-2 can handle unseen objects, backgrounds, and environments.
These images show the different generalization scenarios they tested. In panel AA, we see objects the robot was never trained on. Panel B shows backgrounds it never encountered during training, like that colorful tablecloth. And panel C shows entirely new environments, like that kitchen sink area.
And the results were impressive. Let's look at Figure 4, which shows the performance comparison across these generalization tasks.
This chart really highlights the advantage of RT-2. For scene tasks, most approaches do reasonably well, though RT-2 still edges out the competition. But the real difference shows up in the generalization tests.
Exactly. Look at the unseen objects category. RT-2 with Palm E achieves around 75% success rate, while RT-1 is below 40%. And for unseen environments, RT-2 with PAL IX55B reaches above 50% success, while RT-1 is below 25%.
The paper mentions that on average, RT-2 performs about 2 times better than the next best baselines on generalization tasks, and about 6 times better than the weakest baselines. That's a significant improvement.
One of the most fascinating aspects of RT-2 is its ability to perform chain-of-thought reasoning. The researchers fine-tuned a variant of RT-2 to include a planned step before taking action, which allows for more sophisticated reasoning.
This figure shows examples of RT-2 using chain-of-thought reasoning. For instance, when instructed, "Bring me a drink," the model first plans to pick 7-Up can and then generates the action tokens to execute that plan.
And look at this example at the bottom. When prompted, "I need to hammer a nail. What object from the scene might be useful?" The model responds with rocks and then generates the action to pick up a rock. That's a level of reasoning that goes well beyond simple object recognition or following explicit commands.
What's happening here is that the model is transferring knowledge from its internet pre-training. It knows from that pre-training that rocks can be used as improvised hammers, even though that specific knowledge wasn't in the robot training data.
The paper also mentions another example where the model was asked to recommend a drink for someone who is tired, and it selected an energy drink. Again, that's knowledge coming from the internet pre-training, not from robot-specific training.
It's important to note that while RT-2 demonstrates these impressive emergent capabilities, it still has limitations. The paper explicitly states that the model doesn't acquire any ability to perform new motions beyond what was in the robot training data.
Right. The physical skills are still limited to what the robot was trained on. What's new is the ability to deploy those skills in novel ways based on semantic understanding and reasoning that comes from the internet scale pre-training.
Let's also look at some examples of RT-2 in the language table environment, which is another testbed they use for evaluation.
In these examples, we see RT-2 performing tasks like push the ketchup to the blue cubes and push the blue cube to the Tabasco. These are relatively simple tasks, but they demonstrate the model's ability to understand object relationships and spatial reasoning.
And the paper reports that RT-2 achieved a 90% success rate on the language table benchmark, compared to 74% for RT-1 and 77% for ELEVA, which were previous state-of-the-art approaches.
What I find particularly exciting about these emergent capabilities is that they point to a future where robots can leverage the vast knowledge contained in internet-scale models to understand and interact with the world in much more flexible ways.
Absolutely. And as vision language models continue to improve with more data and better training techniques, robots using this VLA approach should automatically benefit without needing fundamental redesigns.
It's worth noting that the researchers conducted extensive evaluations, about 6,000 evaluation trajectories in total, to verify these capabilities. This wasn't just a few cherry-picked examples, they systematically tested the model's performance across a wide range of scenarios.
And the results consistently showed that RT-2 outperformed previous approaches, especially on tasks requiring generalization and semantic understanding. The gap was particularly pronounced for tasks that weren't explicitly covered in the robot training data.
To summarize the emergent capabilities, RT-2 demonstrates significantly improved generalization to novel objects, the ability to interpret commands not present in the robot training data, and the ability to perform rudimentary reasoning in response to user commands.
And with chain-of-thought reasoning, it can even perform multi-stage semantic reasoning, like figuring out which object would make a good improvised tool or which drink would help someone with a specific need.
These capabilities represent a significant step toward more flexible and adaptable robots that can operate in the messy, unpredictable real world rather than just controlled environments with predefined tasks.
Though it's worth noting that the computational requirements are substantial. The paper mentions that their largest model uses 55 billion parameters, which is an order of magnitude larger than previous models used for direct robotic control.
True, but they did manage to get these models running in real time for their experiments, which is impressive. And as hardware continues to improve and models become more efficient, these computational challenges should become less of a barrier.
Looking ahead, I think this approach of integrating internet-scale knowledge into robotic control systems has enormous potential. It addresses one of the fundamental challenges in robotics: how to build systems that can understand and adapt to the rich complexity of the real world.
Absolutely. By leveraging the semantic understanding and reasoning capabilities of large vision language models, we're moving closer to robots that don't just follow instructions but actually understand what they're doing and why. And that's a crucial step toward more capable and helpful robotic systems.
Well, Casey, I think we've covered the groundbreaking aspects of RT-2 pretty thoroughly. What impresses me most is how they've managed to bridge the gap between internet knowledge and physical robot control through this clever text tokenization approach.
Absolutely, Max. The emergent capabilities we're seeing are just the beginning. As vision language models continue to improve, robots using this approach will only get smarter without requiring fundamental redesigns.
That's what makes this research so exciting. We're not just talking about incremental improvements, but potentially a whole new paradigm for robotic learning.
Thanks for joining us for another episode of Totally Unprofessional Peer Review. Remember to subscribe wherever you get your podcasts.
And until next time, keep your algorithms learning and your robots grounded in reality.
Just remember, folks, these robots may understand internet memes now, but thankfully they still can't explain why the chicken crossed the road, because then they'd be taking our jobs.